to 1, and this one starts from n equals to 0. I want it so it can all sum up under one summation umbrella. So I start writing them out and see if I'm able to tease any pattern now. So the first one here, when you write out from n equals to 2, you come up with 2c times c2 plus 3 times 2 times c3x, and so on, which then you're able to deduce that it is equal to the sum from 0 to infinity of n plus 1 times n plus 2 times c n plus 2 x to the n. And here's just like a little bit of like extra work that I double checked that was in fact correct. And then over here, second here, you can see I did something similar, where c1x plus 2c2x squared plus 3c2x to the 3 plus and so on is equal to this summation. And then down here is this summation. And I noticed that over here you can tell that's minus and minus, so you can really say it's minus the sum of these two terms. So I added them together. So in a way you can say this is equal to 1 times c0 plus 2c1x plus 3c2x squared plus 4c3x cubed plus and so on. And then you're able to see that there's an obvious summation relationship where it goes from n equal to 0 to infinity of n plus 1 cn x to the n. So now I'm happy because I have two summations going both from n equal to 0 to infinity. So I'm able to put them all under one bracket and factor out the x to the power n because it's a common term and equal to 0. So again, from before, I know for sure the summation like inside this term, it has to equal to 0 since in the final to the right hand side is equal to 0. So from that, reduction, blah, 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 I'm able to find that cn plus 2 is equal to cn over n plus 2. So now I need to figure out this, you can tell is a recursive relationship because cn plus 2 is dependent on cn. So whatever two numbers after your sequence is dependent on the two numbers before. So I kind of played around with it. I know I tried n equal to 0 and I tried n equal to 1, and I realized there's a pattern between all the even numbers and all the odd numbers. So over here you can see that for all the even numbers, you have c0 over 2, and then you have c0 over 2 times 4, and then you have c0 over 2 times 4 times 6. So it basically on the bottom it multiplies by whatever your n plus 2. It's like 2 times 4 times 6 times whatever until your n plus 2. And then for the odd numbers, it's very similar except it's 2n, or sorry, not n plus 2 for the even, it's 2n. So for the odd number is whatever you times, but it's 2n plus 1. So now I put them together because I know I set my y is equal to the summation of from n equal to 0 to infinity, cn times x to the n. So I combine the odd numbers with the even numbers, but I tweezed it out still at the end. So I factored out the c0 over 2, so that gives me 1 plus 1 over 4 x squared plus 1 over 4 times 6 x to the 4 plus continue, and then I'm able to deduce this relationship, which is x to the power 2m over 4 times 6 times, recall I mentioned before, times whatever until 2 times 2n at the end. And then it keeps on going because it's a summation to infinity. And for the odd numbers, you have c1 over 3 times x plus c1 over 5, x cubed plus c1 squared. No, plus c1, that's not squared, sorry. The 0, 1, 2 up there is for n. It's for my own notes, so ignore that. So c1 over 5 times 7, x to the 5th, plus all the way down. So then from that, I'm able to deduce the relationship to be x to the power 2n plus 1 over 5 times 7 times all the way to 2n plus 1. And then it keeps on going to infinity. So then from that recursive relationship, I'm able to rewrite my y is equal to C0 times 1, because over here is 1. Let me circle it. So because over here is 1, because it doesn't have an x value, plus the summation of n equals to 1 to infinity, x to the 2n over 2 times 4 times all the way to 2n. And I rewrote it out on a scrap piece of paper and made sure that it matched over here. And then plus the odd number part, which is C1 times x plus the summation of n equals to 1 to infinity, x to power 2n plus 1 over 5 times 7 times all the way to 2n plus 1. I don't think this corresponds to a power series, but it didn't really ask for a power series, just asked for a series. So that is our series solution around 0 in the power of x. And then it's asking me to find the guaranteed radius of convergence of the solution. This one, I kind of reasoned it out because I was looking at the notes on page 2 and 3 of lecture 14. And on that one, it had a of x function in front of the y prime. So usually the form was like a of x y prime minus or plus b of x, a of x of y double prime plus b of x of y prime plus c of x of y equal to 0 or something like that. So in that case, they divided the whole thing by a of x. And then they were able to find what's called a singular point, where usually it's a function below where it would be undefined because you cannot divide by 0. So you find the x value. Usually, so for example, if you have like a of x equals to 1 minus x, your singular point will be x equal to 0. But in this case, there's nothing in front of the y. So there's really just one singular point, I think. It's like my reasoning in my head, which is 0. And if you look at the notes on page 3, so for example, if you have a singular point of 1, then your guaranteed radius of convergence will be the distance between 0 and that point, right? So it'll be 1. So because over here, you don't really have a point where it's not really defined, so it's like defined everywhere. So I logically just think if it's defined everywhere, that means that it is guaranteed to converge at infinity since it's defined everywhere. I'm not sure if that logic 100% makes sense, but that's what I came to a conclusion to.
Okay. Yeah, we're going to talk about an ordinary point, a singular point. Pretty good. Pretty good. Anyone has any questions?
Like, I don't think this one has an ordinary point. Its only singular point is 0, right?
I said, but we're going to talk about.
Okay, sorry.
Yeah, it's okay. Anyone has any question? Okay, good job. Okay, Gregory, your turn.
Sure thing. Okay, can you see this?
Yeah.
Okay, great. Hi, everyone. I'll be presenting from, I think, homework number 13, but change number so it's my own, So the question is, find a power series solution to the differential equation, and it's going to be this, and determine the radius of convergence of the power series. And so we should know that we have a relationship of like y and y prime with summations, and we know that it's, a sum from 0 to infinity with your index being n of a constant coefficient, and x to the n, and so the derivative of that will be y prime. And so here is the format, and we should notice our indices whenever we have these power series because that matters a lot. Is there a comment? Let's check. I did the same modify. Okay, that's great. Anyway, because why do we have this like index of 1? Well, it's because whenever we have our constant term here, what's the chat? What's the talk? Okay.
Oh, no, sorry.
Okay.
Albert was he has a similar question as you. I said
Okay.
that's fine.
All right.
Yeah.
Yeah. So anyway, our index
Sorry,
matters.
we don't mean to interrupt.
Okay. No problem. What's up? Oh, okay. No problem. I get it. Anyway, I'll just continue on. We just want to include this term when we have our y prime, and the derivative of this constant is 0, and so it doesn't appear here, and so we start from n equals 1. And so we can go ahead and move on into substituting our differential equation using these identities y and y prime, which is represented by sums. And so we can go ahead and rewrite, and we have this format. And the next thing we should do is notice the powers of x, because we're supposed to match them. And so on this sum, we have the power of x as n minus 1. And so in order to get that to match with this one, I'm going to replace the n with n plus 1, so that when you plug in n plus 1 to n, the 1 and the minus 1 cancel out, and you're left with n's. And you also have to replace all the locations where you find n in the original summation with that n plus 1. And so we're going to go ahead and do that. And we also have to take note of our index. Since we shifted it by 1, we have to move the index back by 1. And so now the indexes are both 0, and the power on these x's both match. And we can combine the power series since we know how to do that. And we can also factor out this x to the n term out of the series. And we're going to go ahead and be left with this. And we can notice that this coefficient is going to have to be 0 for this sum because the right-hand side is 0. And so we can go ahead and find a relationship between this constant with the next term and a relationship between the current term of the constant. And so if we set this whole thing equal to 0, because this has to be 0 in order for this whole sum to 0, we can go ahead and just look at that part of the equation and solve for our constants. And so we can simplify by dividing on both sides by this n plus 1 and move this over. And so we're going to be left with our constant term with n plus 1 equals to this. And we can go ahead and calculate some next values for this relationship. And we don't want to simplify, because if we simplify, then we'll lose information on what kind of properties are going on with the recursion. And so we want to find a recursion like relation between Cn plus 1 and Cn. And we can go ahead and after we calculate all of that, we can find that our relationship gives us something that looks like this in our values for C0. And whenever we plug in these values for n, we see that we get some relationship with the denominators here. And so whenever you continue to replace the value of the current index, you can find out when you replace using the C0, you end up with n factorial in the denominator. And that's why you don't want to simplify, because you lose information about what's happening. And so after you look at the constant terms, and when you solve for them, this is what you're going to get for n when n is 0, and then when n is 1, you get this, and n is 2, and for n is 3. Whoops. Anyway, so here is our relationship for Cn, as you can find from looking at these terms when you substitute back in for every subsequent term. And so we can go ahead and rewrite our equation since we found the relation after you solve for your values. And after you do that, we can find that given in our text, we know what the summation for e to the x looks like, but here we have a summation when it equates to e to the 2x. And we're also looking for the radius of convergence. And so you take the current term and the next term and find the ratio between them. And since the ratio is infinity, then we converge for all x. And so that's answer to my question.
Very nice.
Thank you.
Very
Any questions?
nice.
No? Okay, great. Thank you very much, Professor.
Thank you.
Mm-hmm.
Let's see. Yaprak.
Okay, I think I'm sharing, right?
It's popping up. Yes, now.
Okay, so my question is, find power series solution to the given differential equation, which is 2t minus 1 y prime plus 2y equals 0, and the radius of convergence. So I let y equal to this summation going from 0 to infinity, and then I get its derivative because like we need that so that we can make the proper substitution. Then I substitute it in, and then I distribute this. So then I got two new summations, and I just move this here. For this first summation, we lost the n minus 1 because this t has power of 1 and then this has minus 1. When you multiply them, you get just t to the power of n. And then I move this 2 inside. And then for this one as well. And then after doing that, we need to combine these three summations into one. But to do that, we need to have the same power of t. So we see that middle one has n minus 1. So I need to re-index this one to the 0. So to do that, I set n equals to n plus 1. So after plugging that in, we get this power of n. And then I was able to, factor out t to the power of n. And then who has a question? Yeah.
David has a question?
Yeah.
Yeah.
How did you get the term on the leftmost side? Remember how you put in the n and it became just t to the n? Yeah, that one right there.
Yeah.
How did you
Okay, so
get it to the next line where you got it to n equals 0 as the first term instead of n equal 1?
I think I had a typo there. Yeah, it should be 1.
Same thing. Okay, so I was just wondering how you would adjust that. Okay.
Yeah, I'm sorry. It's a typo. Sorry. Yeah, I guess it's a typo because, yeah, it's a typo.
Which line? Which line are we talking
He's
about?
talking about this line here because I had 1 here and then 0 here.
Oh, okay. Did you do re-index? Not yet.
Yeah, not yet.
Right. Yeah, so number 1, 2, 3. Right, the third line, right? Okay.
Mm-hmm.
Yeah, you can do corrections. Yeah, on the spot.
Okay, so, so I re-indexed this one in the middle. Then I got this. This stayed the same, just to move inside. And then, since these 3 now have same power of t, they all have n, so that we can combine these 3. I think that's what I did here. That was the logic behind, inside of my head. And then to
No,
for a power.
Hold on a second. So so the third line, 2 summation sign with n equals 0. So your index starting from 0, right?
Yeah.
But the inside form is exactly as above. Above is n, a n, t to the n power.
Yeah, this should be n plus 1.
That's right.
This one also needs to be n plus 1.
That's right.
Here n plus 1, n plus 1. Yeah, and then should I write on it? Here. N plus 1. And then this is n plus 1 as well. I'm sorry, I can't write on it, but yeah, let me tell. And then, yeah, I did the correction there. So I factor out, yeah, no, it's not. This also needs to be
That's right.
n plus 1 as well. Then I can't factor out.
You still can factor out, but you still have t to the first
So that's
side.
Yeah. Should I make corrections then, like present later?
Yeah, you should do that.
Yeah, sorry.
Okay, that's okay. Okay, less 13.2. Liz, are you ready?
Yes.
Okay.
I'm gonna present like a slightly modified version of the number 2.
Yeah.
And I'm not quite sure that I fully understand this, so there might be some mistakes. So just it's loading.
Yeah. Okay.
Can you see it?
Yeah.
Okay. So I have 1 minus x times y prime equals to 2y. Now I'm gonna put the 2y on the left side so I can have it equals to 0. I have 1 minus x factor y prime minus 2y equals 0. I'm gonna call this equation 1. A letter power series solution of 1b of the form y equals to summation of n going from 0 to infinity cn x exponent n, and a y prime, which is gonna be like the derivative of this summation of n going from 1 to infinity and cn x exponent n minus 1. So I'm gonna use those new value of y and y prime and replace them in equation 1. So it's become 1 minus x factor summation n going from 1 to infinity and cn x exponent n minus 1 minus 2 summation of all the value of n going from 0 to infinity and cn x exponent n equals to 0. So I distribute the 1 minus x and then I get my third equation. So equating the coefficient of xn from both sides of 3, I end up with n plus 1 factor of cn plus 1 minus ncn minus 2cn equals to 0. So, and here we have to make sure that n is greater or equals to 0.
You
So
skip something. Hold on
yeah,
1 second. You skip the reindex part, right? Because your equation
yes.
3, you see your index not right consistent. the index has to be consistent to be able to combine those three summation signs.
Yes. I think I don't. I know I don't have this part in this.
So so you can think n, let you want to reindex. If from changing n to n is kind of annoying, you can think I'm going to type in the chat. You could let k, right? You could let n equals to k plus 1. You just use a dummy variable momentarily. Because afterwards, then after you finish, you change k, you change n back to k, or change k back to n. So in this case, you want to change everything in terms of k. So n will be k plus 1, cn will be ck plus 1, x raised by n minus 1 will be x raised by k. You see that? Except the summation sign. Okay. So then once you're done reindex, you change back k, you change back n to substitute k. Yes, you forget about k, you change k back to n.
Yeah, that's why I have n plus 1 times cn plus 1 minus.
Oh, okay. You just skip the steps, right?
Yes.
Okay, I got it. Okay, yeah. I see that. Now I see it. But that's a crucial step.
Okay.
You should show it. Okay.
Yeah, I'm gonna make sure I do this next time.
Oh, what about the second one? The second summation sign also n equals 1. You also have n plus 1, cn plus 1, x raised by n plus 1, right?
The first one is x exponent n minus 1, and the second is the same as the third one, which is just x exponent n.
I'm talking about your index. Your index is starting from n equals to 1.
Yes.
But when you combine two summation signs, the index has to be the same.
But the second term and the third one, they have the same exponent, only like the first one is different.
Right, but we're not looking at the exponent. We're looking at the index n.
Yeah, that's what I mean.
Oh, the index is a summation sign under the summation sign n equals to 1. Above the summation sign is infinity. So this is called the index of the summation sign. Do I make sense?
Can you repeat that, please?
Okay.
Or I don't know if you can write on my.
Okay, so x to the nth power, n is called exponent. But in this case, you see n, the summation sign, n starts with 1, n equals 1 up to infinity. That means n, but we call n index. We call this n index, it's kind of confusing. So this n under the summation sign is called index. So this summation sign is being indexed from 1 to infinity. So if we want to combine the second one and the third one and the first one, the index needs to start
to be the same.
Right, has to start from the same number. Yes.
Okay. Get it. So isn't like the second part is not correct?
Yeah, the second one you need to reindex. You get the x is raised by n plus 1. One minus x. Maybe you want to do the same thing. You fix it, then come back.
All right. Okay.
Okay. All right. Thank you. The reindex sometimes could be very annoying. Okay, so Moises.
Hello, can you see it?
Yeah.
Okay, so I'm just doing question 6 from 14, which honestly it's has the same procedure as number from the problems from number 13, from what I know at least, hopefully. And so here, 1 second, I don't know if it's gonna, okay. So first we need to set y equals to the summation of c and x to the n from n to the 0 to infinity. And so we also have to get the y prime and y double prime of each of them, which we have right here. And I'm just going to explain this now, how I got these numbers. So for this equation over here, this just equals to c to the 0 plus c to the 1x plus c to the 2x squared, and so on. And so when you plug in x to the equals to 0, then all these two, all of them to infinity will equal to 0. So the only one you're going to have left is c to the 0. And so with that, you know that c to the 0 is going to equal to 6. And with c to the 1, it's the same thing. So the derivative of y primes is going to be the same thing, but this is going to be 0 plus c1 plus c2x and so on. So all of the values from c2 to the right are going to have an x term, meaning they're going to go to 0. So the only term we're going to have is going to be c1, which is going to be equal to 2 in our case. So I just want to get that out of the way first. Sorry, it's going to take me a long time to delete all of this. Anyways, so we plug in the y equations into our original equation here, and the indexes are all different, as well as the x exponents. But the x exponents we can just fix by, for example, in here, this one has an x term into it, meaning that x to the n minus 1 times x is going to be equal to x to the n. So that one doesn't need fixing. These two are the same too. So the only ones that we need to fix would be this one. And with that, we just have to add a 2 in here, meaning that in here we also have to add a 2, and in here we have to take out a 2 to, I guess, even it out. I don't know how to really explain it. And now the only problem would be that this term over here is the index is different to these two, meaning that we wouldn't be able to just add them in here like I did. But I looked it up online to help me out, and by the looks of it, if you take out the first term of these two, which would be n to the 0, and then add them separately from this whole parentheses, then you can just put this whole term into here with the index of n equals to 1, as long as you have the first term, which would be n to the 0, and the same thing with this one. So as long as you have those first terms, then it should be fine. Correct me if I'm wrong.
Yeah, that's right. That's right. So this is a good point for Liz and Yaprak. You could do the same. You could do the same because you know you can always evaluate finite terms. In this case, yes, because you can evaluate the first couple of terms. That's
Yep.
n equals 0, n equals 1. Yeah. Yes.
And so this whole term has to equal to 0 right here, and so does this. So with this, we can just solve for C2, which is going to be equals to negative C03. And because we already know what C0 is, C2 is just going to be equal to negative 2, but that's besides the point. And so we just separate this from here and solve for Cn plus 2, which is going to give us negative C over 3n plus 1. And so in here is where I couldn't really fully finish it. I plugged in all n's from 0 up to 5, and we see a even and odd. We have two equations. We have an even and an odd Cn. So how do I explain this? When you plug in n to the 0, this is going to give you C2, negative C0 to the 3. And then in here, because we're just going for even right now, when you plug in n to the 2, it's just going to give you negative C2 over 9, but we know what C2 is, and so you just plug it back in, and so on with n to the 4. We know what negative C4 to the 15 is. Well, we got negative C4 to over 15, but we know what C4 is, just right here. And so you just plug it in. So we pretty much just want all even ends, to say, to be in terms of C0, and all odd terms to be in terms of C1. And so we have these two equations for even and odd, which all contains C0 for even and C1 for odd. And I couldn't come up with a, I guess, general form.
Yeah.
I know there
general
has to be
form
one.
for this term,
Excuse me?
nth term. Yes, the nth term.
Yeah,
Well,
I
you
couldn't
have
really.
it here already. You see, look at C of 2n, C2n.
Mhm.
3, 9 times 3, 15
I
times
saw
9.
it on the worksheet. It was like 2n times double radical, and I'm not really sure what double not radical, sorry, double factorial.
So
And I'm
first
not,
you have alternating series. So you have -1
yeah,
raised
so it should be
by,
like -1 to the n or
right,
something.
you should have this term.
But
Then
obviously C to the 0. But the term that I struggle with would be the denominator.
you have 3. Let's see. If you keep the 3, where does 3 come from? So this is the second term. So 2n plus 1 is 3, right? If n equals
Yes.
1.
Yes.
So 2n plus 1 is your first one. 2n plus 1. Then how do you come up with 9? 9 is 2n plus 1 plus 6. So that's 2n plus 7.
Mm,
The third term,
be 15 times.
is 2n plus 1 plus 2 times 7. Okay. 2n plus.
Yeah, I don't think I'm gonna be able to really do it on the spot because I was like having a headache trying to figure it out. So I kind of just not really gave up, but like made it easier for myself and just
Yeah,
wrote
I
it
think
as
this
it
is
is.
fine. Yeah, I cannot even get
Yeah.
around. But the first one, you have one term, you have 2 terms, you have 3 terms. How would you?
And then for the odd, you have pretty much the same thing, but with I guess.
Yeah. Okay, David. Maybe David has an idea.
Help me out, David.
I think for the evens, I think you'd have -1 to the n, right? So it alternates, and then 3 to the 2n C naught over 2n in parentheses factorial.
Okay, wait, what? 3 to the 2n?
Yeah, 3 to the 2n over 2n factorial, and then you have the -1 in front.
But we don't have a 2. We don't have a 2. If it's a factorial, we have oh, hold on a second. Because the last term will be 2n plus 1. Okay. Okay, so let's see. If it's a 2, 2n factorial, 2n plus 1 factorial, right, David?
Yeah, sorry. Yeah.
2n, so 2, that's 5. 5, 2n, so if it's a 2, that's 5 times 3. But the second term is 9. 9 times 3.
Wait, can't you just make it
Because that's a 7. You see 7 is there. You have the first one, the second one is 2n plus 1, then plus 1, 7. 1 times 7. Then The 15 comes from 2n plus 1 plus 2 times 7. So 1, 2, 3, 4. That would be n minus 2, n minus 2. So n minus 1, so 2 minus 1, 1, 7. Oh, I think I got it. Let me write in the chat.
Yeah.
So it's
Don't remember the last
2n plus 1 time, no, 2n plus 1, and let's see. The second one is 2n plus 1 plus, let's put a plus 1 in the n, plus n minus 1 times 7. Simplify that. Then plus 1. That's what I'm thinking. 2n plus 7. So 2n plus
So
7n, that's 9n.
that would be the denominator? Or
No, second. 9n minus 6, right? Minus 6 factorial. Let's see if this could be right. Because simplify that. So the first one would be, no, that's not right. It's not factorial. Okay, let's not wasting time. If I cannot figure out on the spot, okay, I'm not going to criticize you. All right, I think this is fine. You just do da da da. Okay, you show the pattern as 3. That's times 3 times, 1 plus 3 times 9, 3 times 9. So they differ by 6.
Yeah.
Okay. Anyway, yeah, I think that's good. That's
yeah, and
good.
then I just plugged into C0 and C1 to this equation, and I got this.
Yeah, we can always use the dot dot dot.
Yep. Right here.
Okay. All right.
Thank
That's
you.
good enough. Thank you. Thank you. So the next one, 数线 13.5.
Okay, let me see. I can share. Oh. Cannot find it. What happened?
It was up, now it disappeared.
I have something over here. Or... Let me see. Today I have. Oh, I cannot find it, but I have it. That's a big problem.
We can come back to you, not to worry.
Okay.
Okay, so Albert then.
Okay, so let me share my problem. So I did 13.1 modified. 1 second, it's loading.
Yes, it's up.
You see it?
Yeah.
Okay, good. So the original problem was y prime equals 3y, and we have to determine the radius of convergence of the power series solution. So I started off on the top, changing y prime minus 2y to y prime equals 2y to y prime minus 2y equals 0. Yes, Gregory, it's the same. We both changed a 3 to a 2. I said that when you started presenting, I said, shoot, this is mine. Should I do a different one? But I said, I'll keep this one. This is the one I worked on. So let y equals the infinite sum.
You can easily change it 2 to be something else, right? Change it 2 to be 5.
Should I change it to 5?
Why not? It doesn't change this, the coefficient. It won't change much.
It doesn't change anything. Oh, Israel said his is 5. That's funny. I could change it
Oh,
to 4. The constant actually really doesn't change anything except itself all the way through. So,
yeah. But this is
meaning,
not constant though. This is a coefficient. It's a scalar.
right. The
Mm,
coefficient here, meaning the number
yeah,
doesn't change anything other than it stays
exactly.
constant all the way through.
Exactly.
So
Yeah.
if you want instead of 2, I could say 4 and make believe it's a 4, but
Please make
I don't
yours
think it does
different.
much. Anyway, so y, we're going to let y be the infinite sum from n equals 0 to infinity. Cn x to the n, and y prime be n cn x to the n minus 1, the derivative. Now we substitute in, and our new equation is the first infinite sum, the second one, sorry, the derivative of it, minus 2 times, or 4 times, whatever number coefficient you want to put there, times the original infinite series there. So for the first one, so for y prime, comes out to c1 plus 2c2x plus 3c3x squared, and so on, which we can now change to infinite series of n equals 0 to infinity, parentheses n plus 1, right, starting from 0 as we see, n plus 1 times c n plus 1 times xn. That's supposed to be x to the n. Sorry, that's supposed to be an exponent. X to the n. Okay, so now the reason that we did this is because we're trying to get the bounds to be the same. Because when we did the derivative of y, when we got y prime, we changed, it wasn't x to the n anymore, it was x to the n minus 1, and the bounds changed from 0 to infinity to 1 to infinity. So to make them the same, in order to simplify it, so I took it there on the next line, I put them next to each other, right? The new equations, and then simplified them. I put them together, and then we got x to the n, and then brackets, meaning parentheses, n plus 1 c to c n plus 1 minus 2 cn. And we know the whole thing equals 0, so that has to equal 0. Once we make that equal to 0, we want to figure out what exactly that is. I mean, what is it going to be, the coefficient of x to the n? So I got that c n plus 1 equals 2cn over n plus 1, right, in the middle of the sheet on the right at the end. And then I did it for 0, 1, and 2 until we got a pattern. So I got 2 over 1 C0, then 2 over 2 times 2 over 1 C0, which is 2 squared over 2 factorial C0. And then I got 2 over 3 times 2 squared over 2 factorial C0, which is 2 to the third 3 factorial C0, which comes out to 2 to the n. So Cn equals 2 to the n over n factorial times c of 0. Okay, so that becomes our coefficient instead of the brackets over there in the middle. It becomes our coefficient for x to the n. So I have y equals the infinite sum from n equals 0 to infinity. C to the cn x to the n is the same as 2 to the n over n factorial. If you were to change that coefficient from the beginning to 4, 5, 6, whatever you want, 58, 176, it's going to be that same number that's going to be moving all the way through. So we have the infinite sum from n equals 0 to infinity of 2 to the n over n factorial c0 times x of n. And we know that 2, so you could write it as 2 times x to the n, 2 to the x to the n over n factorial. And we know because of the Taylor series that that is the same as e to the 2x. So we have c of 0 times e to the 2x. And then I used the ratio test to see if that works. And so I did c n plus 1 over c to the n, the limit of that. equals the limit of, right, and then I put that in, I crossed a few things out, and then I got 2 over n plus 1, which is 0, as the limit approaches, as n approaches infinity, which is less than 1, which means the ratio test works. Thus, the radius of convergence of the power series is infinity, which means for every value of x, the function converges.
Okay, let me ask you a question. May I ask you a question?
Yes.
Okay, remember you're going to choose the coefficient 2 to get another number. I forgot which number you choose to change to.
I can't hear, I'm sorry.
Your answer.
There's a lot of noise. What about the coefficient?
Let me see. Hold on. All right. Remember, Gregory already showed with 2y, right? Y prime equals 2y.
Yeah.
You're going to change y prime to be 4y. Let's see if you change your question to be y prime equals 4y to work with. How would your answer change? How would that change your answer?
My final answer?
Solution. Yeah, change your final solution. Change your y. Because okay, you know your
Y would become C0 e to the 4x.
That's right. Okay, that's it.
Right.
Okay. Yes. Okay, that's
good.
my
Thank
question.
you so much.
Okay, good. Thank you. Okay, Liz is ready. Liz, go ahead.
Yes, I think what I had was correct, and because I was
Okay.
kind of skip some the step, I
Okay.
get confused. Before, I just
Okay.
want to share from what I get it. So
Okay,
this
sure.
is from page 7. It's loading.
Okay.
Can you see it?
It's popping up. It's blank.
One second. Oh, it's still showing blank, but if we look at page 7, I don't know if anyone can actually like share this for me.
Oh, I can show you
Yeah,
from the notes.
yeah, page 7 in
Okay, I'll share
page
with you.
13. Yes, please.
Hold on a second. Page 7, right?
Yes.
Yes, right here.
Here, right? So
Right.
what I did is like I changed what I had, which was 1 minus x factored by the sum going from 1 to infinity and times cn x exponent -1. So the only one that's changed it's as the one which has the x exponent -1, they change it so things get can go from 0, but the other one they didn't do like anything. It just went from being 1 to infinity to 0 to infinity, because it's kind of like the same thing. The only difference is like when you have 0 now, this term just doesn't exist. Yes, this.
Talking about this term.
Yes. You see, on the second line, they didn't like transform it into n+1 factored by something.
Right.
It
Right.
stays
So,
NCN.
yeah, you know why? Because why? Right, but this is actually can be changed if we change to.
Yes, it's gonna
Like,
be
right,
n+1.
coefficient. the coefficient won't line up.
Yes.
So if this one start with 1, it works, right? 1, so that's just 1. So there's a C1 start with X, so no
X.
constant term. So this is no constant term. And this one you see no constant term either, because even oh no, this one has constant term.
Yes. So this
This
is the
one
one we change. Yes.
This one has constant term. So this one just doesn't have constant term.
So if
Okay.
you're going from this line to the other line, it just like instead of having n equals to 1, it just n equals to 0. And then
I see.
they factor. Yes.
I see. Right. Okay. So that makes sense. Because our focus is so the focus of this, because this works, but normally we care about the index, you know. But
Yes.
if we
Because I didn't have it. So
right, if we start with x equals 0, we got ourselves into trouble. We have x raised by n plus 1.
yes. So
Okay, I see. So,
Mhm.
so in that case, both you and Yaprak, you don't have to change. Yes, you don't have to change. Okay.
Okay.
Okay. Yes. All right. You find
Gonna,
the notes. Then go ahead.
can I share it and continue from where I stopped?
Yes. Go ahead.
One
And
second.
Yaprak, you can finish yours too. You don't have to change your.
That's
You don't
true.
have to change it because you're just missing a constant term. So who cares
Oh,
about the constant term?
okay.
It's taking some time.
It's coming up. Yes, it's here
Okay.
now.
So now that I have this, I just like isolate the C n plus 1. So it's equals to n plus 2 over n plus 1. So I started at n equals 0. So n is 0, so 0 plus 1 would be just 1. So C1 equals to 0 plus 2 over 0 plus 1, C 0. So this is just equals to 2C0. I did it for a few more so I can try to find some pattern. So C2 is 3C0, C3 is 4C0, C4 is 5C0, C5 is 6C0. So I recall that y equals to the sum of n going from 0 to infinity, c of n x exponent n. And if I replace n by, let's say, 0, 1, 2, 3, 4, 5, etc. So I got like a sum of c0 plus c1x plus c2x squared plus c3x cubed plus c4x4, etc., etc. So I just go in the next line and replace c1, c2, c3, c4, c5 that I calculated. I just replace them in here. So I have now C0 plus 2CO plus 3CO O x squared plus 4 C0 x cubed plus 5 plus 5 C0 x5 plus 6 x4, sorry, plus 6 C0 x5 and dot 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 dot. And I factor out this C0 and I'm left with 1 plus 2x plus 2x squared plus 4x cubed plus 5x4, etc., etc. So I see it's in the form of C0 summation going from 0 to infinity n plus 1 times n exponent x exponent n. So I guess this will be my general form for it. And now I'm gonna go ahead and try to find the radius of convergence. I have a of n equals to c 0 times n plus 1. So I look for a n plus 1. It gives me C0 factor of n plus 2. So I use the ratio test, taking the limit when n approaches infinity, sorry, of a n plus 1 over a n. So I just have C0 factor of n plus 2 over C0 factor of n plus 1. The C0 like cancel, so it's just n plus 2 over n plus 1 when n approaches infinity. So I kind of like factor out like an n. That's why I have like 1 plus 2 over n on the numerator, and on the denominator I have like 1 plus 1 over n. I know when limit is approaching infinity, so 2 over n and 1 over n, those two gonna be 0. So it's just like 1 plus 0 divided by 1 plus 0, and then it's just like 1 divided by 1, and this is just 1. So the radius of conversion is 1.
All right. Yes, nice. Thank you, Liz.
Thank you.
Okay, we're going back to Yaprak.
Yes. Can you see it?
It's getting, yes, it's up now.
Okay, so I was up to this line. So from here on, I just factor out t to the n, and then I set this expression inside the parentheses to be equal to 0, because for power series to be equal to 0, the coefficients must be 0. And then,
but just one thing, hold on one second, just one thing. You don't, right, you can't change this n equals 0. This line, you don't see my cursor probably.
so
You keep n
here?
equals 1. Yeah, the bottom one, yes, right. Right,
Yeah.
you just don't change it to be n equals 0. You still keep n equals 1.
Okay, and then we just
Because if you
go
change
this
it, you reindex, right? You reindex, you get yourself in trouble. You will get a t raised by n plus 1 term. Right, you get a 1 more t there, then that's going to be trouble. So basically, you don't need to reindex, but however, you just ignore the 0 term.
zero term, yeah.
Yeah, because if n equals 0, you get, you just don't change this one, just don't change, just don't index. Because if you're trying to reindex, you just read n equals 0, but you didn't really reindex it. Because if you do reindex, you get yourself in trouble. So just keep n equals 1, just like a list did.
Okay, so we just combine these two then.
You just combine. No, you still can combine all of them.
Okay, but
Because
without changing
what's more
to.
important, right? Because what's more important is your variable has the same exponent, then you can factor out.
Okay. So then this equation is true, right? Then we can just set it equal to 0 to solve for a sub n plus 1.
Right.
So okay, I solved for it, and then I tried to find a couple of terms and terms, and then I see that there's a relationship like this, like for a sub n plus 1, we just take the 2 power of n plus 1 times a naught. So then we see that we can write it like this when we like combine it and then factor out a naught. And then we see that this is equal to this summation from 0 to going to infinity. So this was the answer for the first part, like finding power series solution. And then for the radius of convergence, we do the ratio test. And then, so for the ratio test, we also need an. So we can find that by plug it in n minus 1 to the n, and it turns out this. And then after like putting a sub n plus 1 and an to this ratio test, we see that some terms are being canceled out, like a naught goes out, and then 2 to the n goes out, and then we get this ratio 1/2. And then since 1/2 is greater than 0 and less than infinity, then we can say that this series converges if absolute value of t is less than 1/2 and diverges for absolute value of t being greater than 1/2.
Okay, nice. Thank you.
I have a
Maybe,
question,
yeah.
but like more for you, Professor.
Yeah.
On the part where she you said you could ignore the 0 term. I'm sorry, can you scroll up a little bit? Yeah, thank you. Over there.
Yeah.
Why was it that she was able to switch the index from n equals 1?
She cannot. That's what I was telling her.
Okay, but
She
why
cannot.
does it still work?
Keeps n equals 1. Because what if n equals 0? If n equals 0, you see, if you don't reindex, just think about this. If n equals 0, you just have a constant term, t to the 0th power.
Okay, no, but like when you put in the
We
n,
just
like
don't have a constant term. Right. No, that's what I was telling her. She cannot write n equals 0 here. You
yes,
probably don't see my cursor. She
yeah,
just keep this one. She just keeps n equals 1. So
and
n
then
equals 1.
you're allowed
And
to
this
still
power
do that.
series, yeah, because think about it. This power series it just doesn't have a constant term. It starts with t raised by 1, t raised by first power.
Oh, okay. Because then you just have t to the 0, right? And then okay.
Right. You just have a1. You start with a linear term, a1 t to the first power.
Yeah, because I kept getting t to the n plus 1, and then I couldn't
That's
factor
the
it.
trouble, right? Right. Because I realized too, right? When Liz was talking about my page 7, I realized that if you get into, the t raised by n plus 1 or x raised by n plus 1, then you get yourself in trouble.
Yeah. Okay. Thank you.
You're welcome.
So it only works for the power of n, right?
Yes, because that's more important. Because you think about it,
Yeah.
what's the difference between if you n start with 1, then so our power series for this one start with t raised by 1. We just don't have the constant term, but that's fine. That's fine.
Okay.
So the thing is, you don't need to reindex this for this one. You just keep n equals 0, n equals 1. Yeah, you do need to reindex when t raised by n minus 1 or n minus 2, because you want to have t raised by n.
Yeah, like here, we need to reindex.
That's right. That's right. For t, we already have t raised by n. We don't need to reindex. Liz is saying something. Let me see. Equals 0 because you time by 0, the term just disappeared. No. No, in this case, if we reindex, we get n plus 1, right? Think about k plus 1.
Yes, I know, but I'm saying that isn't it like, can we say that this is one reason that we don't like do the index thing? We just keep change like the 1 to 0, because if we start at 0, either we start at 0 or we start at 1, we'll still have the same thing. But when we have 0, it's like 0 times a0 t exponent 0, so this just becomes 0 and disappear. And then when we have 1, this is where you start getting value for the term.
Well, if we reindex n equals 0, so the n multiplied by n, the n will become n plus 1.
Yes, I know, but I'm not talking about like doing the reindex, because if we do it, we're gonna have like a n plus 1. So I'm saying that, let's say we have like n a n t exponent n, either we start at 1 or we start at 0, it's gonna be the same thing, because when we replace n by 0,
Right.
this just disappear.
You are right. Yes. Yes. Okay. Let's see. Shuxian, are you ready?
I guess yes. Let me see.
Okay.
I don't think so because I don't know how can I share the time.
Okay.
Only the email, so I download it, but it didn't show up. So that's why I don't know. Maybe next time.
Okay.
Okay,
Right.
thanks.
So then, okay, Kyle.
Hello.
Hello, Kyle. Is this your first time?
Yes, actually. Share application screen. Let's see. Share screen, I guess. Can you see my screen? Oh, okay.
It's getting up. Yes, now.
Okay. Yes, I did another modified version of question 1 from problem set 13, but I changed the number to -8. So I have y prime is equal to -8y, which you then can rearrange to be y prime is y prime plus 8y is equal to 0. And then you can say that y is equal to the power series from n equal to 0 to infinity of c n x to the n. And the derivative of that for y prime becomes n equal to 1 to infinity of n c n x n to the n minus 1. So you substitute both of those into the equation, and you get this, and then you have to line up the indexes for the coefficients. So in my case, I was able to do that by adjusting the derivative portion to be n becomes n plus 1. The n minus 1 on the x becomes just n, and then the index goes back down to 0, so they're lined up, and now you have the indexes or the coefficients combined here, and you can factor out the x to the n, and then you can set all the coefficients or the summation of the coefficients equal to 0 here, and solve for c to the n plus 1, which I actually made a small mistake here. This was supposed to be negative n c to the n, so I sort of corrected it. So you get c to the n plus 1 is equal to -8 c to the n, c sub n over n plus 1, which is the reoccurrence relation. And then I plugged in n equal to 0, 1, 2, and 3 in order to determine the pattern. And I had to do some corrections here because I forgot the negative when I first did it. But you end up with that c to the n is equal to, and I'll see if I can zoom in here because I added this correction. Because of the negative, you have to have the -1 to the power of n, and then 8 to the n c naught over n factorial. So that's the cn, and then you can solve for y of x, was equal to the summation of cn x to the n, and you plug back in the c to the n that you found, and using the Taylor series, you can determine that this is equal to e, in my case, e to the -8x. So it's y of x is c naught e to the -8x. And then I solve for the radius of convergence, where rho is equal to the limit as n approaches infinity of c naught over c naught plus, or cn over cn plus 1. So you solve that, and you get that the series converges for all x.
Okay, so let me ask you a question. So you can change the coefficient from 2 to be 8, right?
So I think in the original question it was 3, and I changed it to -8.
Oh, okay, okay. You change to be -8. All right. Okay, thank you. So Su Xian, you are ready, I guess. Okay, I think Su Xian is the last one, right? Oh, Israel, you want to present something similar to that?
So sorry, cannot share. So sorry. So
That's
I
okay.
gave up. I gave up. Thanks. Sorry.
Okay. Okay. Okay, Israel, then you are the last one.
Okay, give me a sec. I actually forgot to do the radius convergence, and I just realized that.
Oh,
That's unfortunate. Oh, I'm not
you remember now?
presenter.
Oh, okay.
No, I wasn't able to do it in time. I just realized that I completely forgot about that part. There we go. Well, this will be the 4th time we'll cover this number 1.
Okay.
So essentially, the only thing I modified was I just made it -5. Well, I moved it to the left and made it -5y. So essentially, what we do always is we substitute y prime to be the summation from n equals 1 to infinity, n times c of c of n x n plus 1, or no, pardon me, -1. And we also substitute y equals the summation of c of n x to the n. Obviously, plugging that in, we get the summation of n equals 1 to infinity, n times c of n times x to the n minus 1 minus 5, the summation of c of n of x of n equals 0. So then, of course, we wanna line up, or index the summation so that we can add them together easily, which gives, of course, for the first term, because it's not the exact same. So doing that, we get the summation of n plus 1 times c of n plus 1 times x of n. And plugging that back in, we get the summation of x of n plus 1, c of n plus 1, x of n minus 5, the summation of c of n times c x to the n. Now, of course, we got to solve for 0, since the only way the summation can equal 0 is if the the terms equal 0. So doing so, we do c of n plus n plus 1 times c of n plus 1 plus actually, I made a mistake here. It's supposed to be minus 5c of n, which would make it then positive 5c of n over n plus 1. So obviously, it's a very common one and very easy to solve. I didn't really do the solving it making consistently c of o. I just knew it was 5 to the n power over n factorial times c of o. And then simply, putting it into the y of x, it makes it the summation of 5 to the n over n factorial c of o where times x of n. So obviously the only terms that we need to keep inside the summation are 5 and x to the n over the n factorial, which of course always comes to, e to the 5x would be my solution, times c of o.
Well, but you made a y equals to negative, or no?
Yeah, no, I kept it positive technically. So from the original one where it was y prime equals 3y, I made it 5 and I just moved it to the left.
I see.
Yeah, so then it would just stay positive.
So I'm missing some minus sign here.
Yeah, I accidentally forgot the sign on two of them.
Sign here.
Yeah.
Okay, all right. Yes, Suxian, you're ready?
Yeah. Let me see. Can you see it?
Yes.
Okay, thank you. So today I present like 13.5 and find a recurrence relation for Cn in terms of the C0 and C1 and the initial conditions to find C0 and C1 and hands on and find the power series solution to the initial value problem. So the equation is y double pi plus 9y equals 0 is the initial value is y of 0 is 0, y pi of 0 is 6. So we know the y is like a power series like this term, and y pi over here, y double pi over here. So we know the y double pi plus 9y equal, we need to find like a y double pi equal this one, and then the y is equal this one. So we have this term plus 9 and multiply this part equals 0. So we talk like a whole 9 and then the line up and index. I choose like a background, so I don't know what's his name. So I took the easy way because here is x power n minus 2, and then another term is xn. We cannot factor out, so that's why we need to make that xn minus 2 equals 0. So I took like n is equal n minus 2. No, n plus 2. So over here, x power the n plus 2 minus 2 equal n over here. So Cn is n plus 2. And then the n minus 1 is n plus 1. And then the n is n plus 2. And then here, n equals 2 is n equals 0. So I get the index. And I use this one and replace this one. So I get the new equation, power series and equation like this. So, and then I factor out like x, like power n term. So I had coefficients and then like n plus 2 over here like this equals 0. So if I take this one is 0, so the coefficient suppose equals 0. And then we know all like n and then greater than n equals 0. So we and then the solve this equation is C n of n plus 2 equal negative 9 Cn over like n plus 2 multiply like n plus 1. So we suppose and then get this equation and then find the like a pattern. So if like it takes like n plus we know that n greater than and equals 0, we suppose to have the 0, 1, 2, 3, 4, 5 and the plug in get the pattern. But if you do that way, we cannot do that. So that's why I separate two things and then take the n is even number first. So I get n equals 0 and get C2, this one. So n2 and get this one. And then you know over here, so when you plus the 2 over here, you get the C2 over there, and I plus in the C2 over here. So I get the final one, I miss one, this is negative 1, like a power 2, sum 92, C0 over 4 factorial. So N4 is the last one, the final over here. So I get the pattern is like here, C2n equal -1, like power n times 9 power n times C0 over 2n factorial. This one is like you take like a power series. This I think is like a cosine 9x over here like this. So and then we have like even number. So after that I have R numbers. I get the pattern. So n is 1 and C3 is here. N equal 3, Z5 is here, because if you plug in this number to this one, the equation over here, we get the pattern. Let us see, 2n plus 1 equal -1 power n times 9n times C1. So we have the C0, we have C1 over here over like 2n plus 1 factorial. I'm missing this like notation. So over here factorial. So we know this factorials over here. And then the like C1, we go about ignore like C1. We get this one's like a power series is sine like a 9x. So that's why we get the like general solution is y equal C not cosine 9x plus C1 sine 9x. So we have like initial value over here. So we have y pi over here. So we suppose get the y pi derivative. The first derivative is -9 cosine sine 9x plus 9 C1 cosine 9x. I plug in the initial solution over here. I get C not equals 0. And then the y like a pi initial solution over here. I get the C1 is 2 over 3. So that's why I get the unit like a solution is y equal 2 over 3 sine 9x. That's my final solution.
Great, great.
Thank
So nice. Okay, yeah, I like this question. This question is nice. All right, anyone else like to present? All right. I won't be able to finish talking about 14, but let's start. Let's start. So note 14 is about the series solutions near ordinary points. Let me read this. So a general homogeneous second order linear differential equation with analytic coefficients. For example, as a function can be represented by power series. Okay, so this is one typical way to understand analytical mean. Analytical means function can be represented by a power series. And it has a form of this, a function of x times double prime of y, another function of x times y prime, another function of x times y equals 0. We have seen this before, right? It's not, if this is not equal to 0, we can divide every term, 3 terms by it, and we can rewrite it like this. Right? We use P representing B divided by A, Q, C divided by A, so we have this kind of form. So we're interested in finding out what happens if there's a point, you know, such that the denominator, the A of x is 0. Because if A of x is 0, we won't be able to go from this step to this step. right? If the coefficient of y double prime is 0. Let's see an example. So we have this x squared y double prime, y prime, x cubed y equals 0. If we divide it by this such a of x, which is x squared, we get this. Right? So we have 1 over x squared here. And we call it p of x. So p of x equals 1 over x squared. Is not analytic at x equals 0, right? X is not in the domain. We won't be able to present this function at 0 as a power series. Definition. So because of such a situation, let's make some definitions. If we consider the equation such x equals a is called an ordinary point. So compare versus singular point, which Anchi mentioned earlier. It's called ordinary point of this equation. And of this equation, if P of x, Q of x are both analytic at A. If not, if this is not the case, and we call A a singular point. A singular point. So we see in this case, 0 is a singular point for this. Right. Zero is a singular point, and all other points are ordinary points. Let's see this example. So have such equation. So a of x is x squared minus 1, b of x is 3x squared plus 1, c of x is 5 minus x. And 0 is not ordinary point, but plus minus 1 are singular points. Because if we divide by a of x, right, x squared minus 1, a of x becomes a denominator, then we see clearly plus minus 1 are singular points. So P of x and Q of x don't have convergent Taylor series around plus minus 1. So we won't be able to write them as a power series. But they do, if x is not equal to those two, we are able to do that. So we call plus minus 1 singular points, and the other points are all ordinary points. Theorem. Suppose A is an ordinary point of such equation. Right? P is the same thing, Q is the same thing, are analytic at A. Then the differential equation has two linearly independent solutions, each of the form. Linearly independent. So y of x equals to infinite power series, right? So when a is 0, we see just Cn x raised by n. But a can be any other number. So the radius of convergence is at least as large as the distance of A to the nearest real or complex singular point. If anyone has any question at any point, let me know. Let's see this example. We want to determine the radius convergence guaranteed by the previous theorem of this a series of solutions. So this one. So a of x is x squared plus 25. B of x is x. C of x is x squared in the powers of x. What if it's in powers of x minus 4? So if we write P as B divided by A, we have X divided by X squared plus 25. Q is C divided by A, it was X squared divided by X squared plus 25. So P and Q has singular points at the complex numbers, plus minus 5i. So if we use powers of X, A0, and the radius of convergence of a series solution is this, right? Because X minus A is 0. So that's just X raised by N. The radius convergence is at least 5. See 5i and minus 5i, the typical value. The distance between 0 and the nearest singular points of plus minus 5i. If the series solution is the powers of x minus 4, then a equals to 4. The distance between 4 and plus minus 5i, this picture, is square root of 41, right? Because here distance is 5, here distance is 4, 4 squared plus 5 squared, square root, so that's 41. So this hypotenuse shows us the difference, the radius of a convergence for when a equals to 4.
I have a quick question.
Yes. Yeah.
So
go ahead.
When I did the homework, how I interpreted it is when it divided by a of x,
right,
on the graph, you're basically graphing the solution for when the denominator is undefined, right? So if you're dividing it by a constant, so if it's just a 1, that means the entire vertical axis is defined, right? So
that's true, yes, if it's 1, yeah.
That means it's guaranteed to converge like along the whole axis, which is infinity, right?
That's right, yes. Okay. Yeah. Let's see this example. Find the general solution in powers of x of this. So this is a of x, b of x, c is constant. Then find the particular solution with those two initial values. So the only singular point is plus minus square root 2, right? Because if we divide by a of x, and we have 5x divided by, so the p of x is 5x divided by x squared minus 2. And the q of x is 4 divided by x squared minus 2. So clearly, the singular points are plus minus square root 2. So the radius of convergence of the solution should be at least this much. Yeah. So this is for 0, right? X, a value is 0. So this is y, then y prime power by power root, y double prime power root again. So substitute back into the equation. So get this. Then, so x squared go into this x and minus 2. So let's change that to be x raised by n. Then negative 2 times that. Negative 2 we can multiply inside the summation sign. So get negative of summation of this term. But this still have n minus 2 as exponent. Then we have this one, 5x and minus 1. Well, multiply 5x inside. So x times x raised by n minus 1. It just x term becomes x raised by n. Then we have this one. 4, we can put it inside the summation sign. So now we can start the first and third sums from n equals 0, since that won't change the values of each expression. right, because here we have x raised by n. So that means this power series start with x squared, which just doesn't have x raised by 1 and the constant term. That's fine. That's fine. And this is the same thing, right? So this is n start, oops. So this one has n start with a 2. 2 minus 2, that's 0, right? So now, so this one we don't have to change. This one we have n starting from 0. But this one starting with 1. But this is lined up, x raised by n, x raised by n. Oh, I see why. I see why Yaprak changed her from 1 to 0. So this is type O. This is not good. This is type O. So this still has n starting from 1. All right. Because going from here to here. Oh, okay, that's fine. Because if n equals n start with 0, that's what Liz was talking about, right? If n start with 0, because we have n here, so that's a 0. So we're just adding 0 to this series. So this is different from Yaprak's, I guess. If we have n start from 0, right? This just didn't change anything. But I would keep this one. I would keep this n equals to 1, right, to make more sense. Because if this n equals 1, you know, my power series just start from x raised by 1 with some coefficient. That's perfectly fine, right? So let's keep this one. Let's treating this one as type O. All right, we don't really need this. And this one is the same. It's the same. This is still n minus 2 here. This one, I guess, is the same thing. Same, you know, same thing says, you know, if the sum from n equals 0, it won't change those values, right? Because n equals 0, that's 0. N equals 1, this term is 0. So the powers of x in the second term don't line up with the powers, so we see, because this is n minus 2. Minus 2. This is n. So all of this is like reindex. Because when we deal with the summation sign, when we want to combine summation signs, we need to have the same index. We need to have the index being consistent. But sometimes we can always think individual case, right, to make sense of it. So after doing all that, so we get this one. So this is our goal. We want to line up the x to the nth power, so we could factor out all the coefficients, because a power series equals 0. That means all the coefficients are 0. Then from there, we're trying to find the relationship among the terms. So indeed, if we simplify this, in the end, we did find a relationship between not two consecutive terms, but alternate terms. So n plus 2 term and the nth term has such relationship that's scalar by this. So n plus 1 term is such a scalar of the nth term. And for even one, you know, we evaluate some 2, 4, 6 up to 2n. So get this pattern. For the odd one, So this is for the even ones, right? So the nth term, the general term is such. Okay, so, just to simplify this writing, we can always define something to write the expressions with a simple version. So in this case, we're saying, okay, let's redefine 2n plus 1 factorial divided by 2 raised by n divided by n factorial. So let's just redefine this with this simpler expression, but with a double exclamation mark. So in that case, we can write, in this version. So we have 2n minus 1 with a double factorial. Well, this is just temporary definition, okay? Temporary definition for the nice looking expression. You don't have to do this, right? You don't have to do this. So, but in any case, so we find for the even terms, we have such relation, right? We have such a relation. So the 2nth term is a scalar of C naught. Similarly, for the odd version, we do a couple of terms, try to find the pattern, and indeed, we did find the pattern. So we still use this temporary notation. So we have this 2n plus 1 double factorial divided by 2 raised by 2n, or 4 raised by n divided by n factorial. So the general solution would be a combination of those two. Yeah. And the even terms, so multiply by a scalar, and then the odd terms multiply by another scalar, or you can use dot dot dot. Sometimes, like right, like one of the presentations, if it's difficult to find the nth term or 2n term or 2n plus 1 term, you can always use dot 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 to show the pattern. So we're given initial values, right? Y of 0 is 4, y prime of 0 is 1. So you can plug in that. Right? So that means C naught is 4, C1 is 1. So you can plug in C naught. And C1 is 1, 1, just we don't have to write it. So the solution is such a unique solution for the given two initial values. Or we can use dot dot dot, right, to represent this series. Anyone has any question? Okay, 5 more minutes. Translated series solutions. So in the previous example, we're given initial conditions in terms of y of 0 or y prime of 0. Oh, y of a and y prime of a when a is not 0. So we will need to find a general solution as a power series around 8. So we will have such form, x minus 8. It's not x minus 0. So one way around this is to make a substitution, like z equals x minus 8, right? Z. So instead of using z to the nth power. Let's see this example. So we want to solve this initial problem with an initial value y of 1 equals 4, y prime of 1 equals 1. And a of x is this, t minus 1 squared with a double prime. And b of x is 5 times t minus 1. C of x is 4. So we want a solution to have like a t minus 1, right? T minus 1. So a is 1. So we want to substitute t minus 1 into another variable. Let's call it x, right? Then x equals to t minus 1, which means t equals to x plus 1. So we just substitute t into x plus 1 for everywhere. So t squared becomes x plus 1 squared. Negative 2t becomes negative 2 times x plus 1. Then simplify this. So we get x squared minus 2. So this is a of x. B of x is 5 of t minus 1. Well, x equals to t minus 1, so that's just 5x. So the equation, before t minus, so this is t minus 1 squared, t minus 2, t minus 1, t squared minus 2t minus 1, that's a of x. B of x is a c. Now becomes x squared minus 2. So this is a of x. Before was t, a of t, right? A of x, b of x, c. Now with this initial condition, which we have solved previously. So the solution to the original problem is what we get when we substitute x equal to t minus 1. Right now we can change back t minus 1 for x. So that just becomes this. So then y of x is the y of t now. So we always do this in mathematics, right? Anyone has any question? Okay, we'll leave the rest for next class. Not too much, so that's gonna be added to. Yeah, added to next class. All right, anyone has any question?
So we should start the homework anyway, right?
Yes, please.
Okay. Well, thank you. Have a good night.
Oh, you too. Have a good night.
Hi, Professor. This is Susan. I have a question.
Yes, Susan.
So for homework 2, remember, I had a problem when I submitted the first homework. You said it wasn't showing. So I resubmitted the homework again. But
yes.
yeah, but on Blackboard it's still saying that I don't have that I have a 0. It's just saying nothing shows up. So I don't know. Were you not able to get the new submission?
Resubmission. Hold on a second. So, yeah, resubmission for Susan only. Let me see. Susan, let me find you. Yeah, right here. You don't see it, right? But I see it. I see on my end. So you don't see on your end, you mean?
Yeah, on Blackboard it still says I have a 0 for that homework. So that's why.
Oh, okay. I see your point. Because I haven't moved it yet. So I need to move this resubmission to homework 2.
Okay.
Okay, that's good reminder. Let me do it right now.
Okay, thank you.
You're welcome. You're welcome.
Mm-hmm.
Resubmission for student only. So that's homework 2. Right here. Yes. Okay, I have changed it.
Okay, thank you, Professor. Have a good
you're
night.
welcome. You too. So I don't need that anymore. Also, I need to move those two. Yes. Oh, thank you. Have a good night. Caps are good. Have a good night.